So in the last part, we did talk about some of the instructions like R3, and I know maybe some of us were not aware of what we were talking about. So I want us to look at what is it that is always in the 8051 microcontrollers, especially with the reference of the registers of 8051 microcontroller. So when you talk of the 8051 microcontroller, it is a widely used register. It has got widely used registers these ones we will later illustrate by looking at the instructions like move, add, and also other assembly and machine language, and to define such mnemonics like the opcode, mnemonics, opcode, and operands. So if we look at the 8051 microcontrollers, the 8051 microcontrollers, as we had said earlier, it is an 8-bit register. So when you say that it is an 8-bit register, so what we are simply saying is that the structure of it looks like this. Like then here we have D0. We usually start with MSB, D7, D6, D5, D4, D3, D2, D1, and D0. And this one is now what we usually have for the register of 8051. And they are always, basically the registers are always used to store information temporarily. And the information, this information can be, that could be a byte of data that is supposed to be processed, or an address pointing at the data to be fetched. Mostly, the majority of 8051 microcontrollers, the 8051 registers, as we had said, are 8 bits. And what that simply means is that when you talk of the 8051 microcontrollers, then we are simply dealing with one data type, and that is the 8 bits of data. And the 8 bits of data, just as shown, usually has MSB, the most significant bit. MSB is the D7, while the LSB, that is the least significant bit, is the D0. So that is now what we have for that. So we can see that these ones are 8 bits of data, with the most significant bit being D7 and the least significant bit being D0. And with this data type, with the 8-bit data type, any data that is larger than 8 bits will have to be subdivided or broken into 8 bits chunks before it is processed. Since there are a large number of registers in the 8051, we usually have large number of registers in 8051, but the most commonly used registers are the ones that we are going to show. So the most commonly used registers, we usually have the registers. So we can divide them into two. The first one is what we refer to as the 8-bit registers of 8051. So we are going to start by looking at 8-bit registers of 8051 microcontrollers. 8-bit registers of 8051 microcontrollers. So these ones are several. Maybe we can look at that structure. So these ones are the 8-bit. The first one up there we have A, then we have B, then we have R1. Oh, no, not R1, but we start with R0, R1, R2, R3, R4, and they should be up to R7. No? So that is now a representation of 8 bits of register. So in the earlier instructions, we talked of R3. So this is the memory location that we were talking about. And again, we also have other registers, that the 16-bit registers that are used. I'm not saying that these ones are all the registers that are always used, but rather what we are saying is that these are the commonly used registers, right? The general purpose registers that are always used. So when you talk of the 16-bits, we are simply going to talk about the DPTR. So for 8051, 16 bits registers. So in this case, we can divide them into two so that each part represents 8 bits. So this one we can call it DPTR, which means the data pointer, and the data pointer high, and data pointer low, so DPH and DPL. Then we can also have another 16 bits of that nature. So this one we have PC. So we call it PC, which is the program counter. Program counter. So those are the 16-bit registers that we can talk about. So those are the 16-bit registers that we can talk about. So we can always, just as we had stated earlier, we can look at how these particular instructions are always, how these registers work. We can look at the registers vis-a-vis the instructions. And I stated earlier that we are going to look at them in terms of two simple instructions that are always executed by 8051. And that is the move instruction and also what we call the add instruction. So we are going to start by looking at move instruction. Move instruction. So we are going to look at move instruction. So when you talk about the move instruction is always written as MOV, that is move instruction. It's always written as move instruction, and it is simply stated as move instructions, and its main work is always to copy data from one location to another. It copies data from one location to another, and it has the following format. We usually have move, then destination. We have move, destination, comma, source. And what it does is that it's supposed to copy source to destination. It copies source to destination. So that is what move instruction is all about. So this particular instruction usually tells the CPU to move, or in reality, copy the source operand to the destination operand. So the source is here, like in another earlier case we said move R3 maybe hash 55H. So it means that you are moving 55H, which is an immediate data that is provided into the destination, which is now maybe it can be a register or whatever destination that is applied. So we'll also look at that one further when we'll be looking at the modes of addressing. So if we, for example, if we have an instruction like move A, R0. So this instruction simply means that you are copying the contents of register R0. So from the diagram we had the register R0. So we are simply copying the content of register R0 into A. So that one means that at the end of the execution of that particular instruction, it means that both register A and register R0 will have the same instruction. They will have the same instruction. So after this instruction is executed, register A will have the same value as register R0. So the move instruction will not always affect the source operand. The move instruction will not always affect the source operand. So we can look at a simple program here. We can write a simple program here. Then we follow it by what we refer to as the trace table to see, to illustrate on the move instruction. So let's have this so that we can see what the move instruction is about. So the program is shown. So we can talk of a program like this: move A, comma, that one 55H. That one means you load value 55H into register A. Then move R0, comma, A. Then it means that you copy contents of A, copy contents of A into R0, and that is to say, now it means that A will be equals to R0, which will be 55H. Then the next instruction we can talk of move R1, comma A, which means you are copying the contents of A into R1. Copy contents of A into R1. That one means that A is going to be equals to R0, which is going to be R1, which is equals to 55H. Then we can talk of move R2, comma A, and that is to say copy contents of A into R2, and that is to say A is equals to R0, R1, R2, which is 55H. Then we can have move R3, comma, hash 95H. Then that is to say load value 95H, load value 95H into R3, and that one is to say now we can say now A is going to be, we can only talk of R3 because it is the one that is affected. Then you can say R3 is 95H. Then we can also talk of move A, comma, R3. Then this one simply means you copy contents of R3 into A. And that one means that A is now going to be R3, which is equals to 95H. So those ones are some of the instructions that we can talk about. Now we know we have register R0. So this one will majorly talk about it when we'll be talking about the addressing modes, and we usually refer to it as immediate. The moment you see that flash, that hash, we usually refer to it as pound sign. So the moment you see the pound sign, it means that we are talking of register. We are talking of an immediate data, which means the data that is supposed to be moved is already given in the instruction itself. So in that case, that is what we have for that particular program. So I want us to develop what we can refer to as a trace table for this particular program, for the program that is there, so that we can see what is there in all these memory locations. So the first thing that you are supposed to do is to identify the memory locations. So you can identify the memory locations. So maybe we will not need this now. So we want to use this to form a table, to form a trace table that we are going to use in order to see how these particular instructions work, and also to check on how the registers work. So we can have a table here where maybe we can talk of that one. So the first thing that we need to do, we need to look at the registers that are affected in each and every instruction, like move R3, one was move. That last is move R3, comma 95H. So we are going to look at what each and every instruction. So we are going to look at what memory addresses that are affected. So the first memory address, we look at the first instruction. So maybe we can have a table that way. So in this table, we can talk of the instruction. So these are the instructions. And after that, we can talk about the memory locations. We want to look at the memory locations. So we can talk of the memory locations. So the memory locations, maybe we can have something like that. Then from here, we can look at this instruction, the first memory location that we can see. We can see right there is register A. Then in this one, we have R0. In this, we have R1. A is already repeated, so we are not going to write it again. R2, A is already repeated, we are not going to write it again. R3, and A is also repeated. So that is what we are going to look at when we are developing a trace table. So our trace table, if you look at that, our trace table has got 5 memory locations as per the instruction. So we are going to look at how each and every instruction is going to affect the memory location. So like for example, if we talk of the first instruction, move 55H into register A, which means at the end of this particular instruction, the only register that will be affected is that, and what will be moved there is 55H. It means that that one and that will not be affected. Those ones will not be affected, so we will not have those particular registers affected. If we go to the next one, it means A already had 55H, so it's going to copy the content of A into register R0. So it means that at the end of that instruction, again register R0 will also have 55H, while these other registers are not affected. When we come to the third instruction, we have A, which is already 55H, will be moved, so R0 will remain 55H because the instruction does not affect it, and now 55H will again be in R1, and then those ones are not affected by the instruction at all. The next one, we are going to talk about this instruction, RA, so we talk of A will still have 55H because it was not affected. R0 will have 55H, not affected. R1 will have 55H, not affected. R2 will also now have 55H because the content of A will be copied to R2, and then this one is not affected. Then we can talk of R3. So when we come to this, it means that A is not affected, R0 is not affected, that one is not affected, so it will still have that. Then R2 again, we will still have 55H. Then R3 will now have 95H because 95H, it should be pound sign. 95H should be copied to that. Then at the end of this instruction, move whatever is in R3. So whatever is in R3 will be moved to A, which means it will overwrite what was initially there, and at the end of that, it means that our A will now have 95H, while the rest will remain 55H, and R3 will also have 95H, while R2 will still remain 55H. So that one is how the trace table for those particular instructions can be obtained. So I'm just going to give one example again. If you want to look at another example or maybe further, how it can be done, you can also go to the website, that is EES.education. So you can also go there and see what maybe further illustration on that. So I want us to look at the second instruction, that is the instruction on add instruction. In order to understand the registers, this ones we're just doing in order to understand further the registers that are used in 8051, because the 8051 is very because 8051 registers, we've talked about the registers, but now we are just trying to illustrate how these registers can be used. So we are going to look at the second important instruction that is going to be used in order to illustrate the movement of data into 8051 registers. So the next instruction that we are going to talk about is add. Add instruction. Add instruction. Add instruction. So when you talk about the add instruction usually has the following format. We have add, then add A, then source, which means you add source, you add the source operand to the accumulator. Add the source operand to the accumulator. The accumulator is simply the register A, and the register A is always used for logic and arithmetic operations. So anything that involves logic and arithmetic operations, then the register A has to be called upon. So we can talk about, maybe we can have a small program. So if we have the add instruction, before we can have a program, add instruction usually tell the CPU to add the source byte to register A and put the result into register A, which means at the end of that instruction, you are adding what is there in the source to register A, and the result will again be stored in register A. So maybe we can give a small example on how to add two numbers and then see how the trace table will look like. So we can have a simple trace table for that. So maybe we can have this program, an example of a program like that. That's a small program. We can talk of move A, comma, immediate data, 25H, then it means load 25 into A. Then we can talk of move R2, comma, that 34H, then it means load 34 into 34H into R2. Then add A, comma, R2, which means add R2 to accumulator. That is to say, A is going to be A plus R2. So maybe, again, this is a simple one. We can develop a very, very fast trace table for this, just the same way we did for the first case. So if you have this, we can maybe remove the comments here so that we can form a table very, very fast in order for that. So you can have that. So in this case, it will be the same. This side we have instruction. Then here we have memory location. Then we have memory location. Then from there we can look at the registers that are affected. So the first memory location is A. Then we have R2. I think we only have two. A and R2. So we have that and R2. So the first one, we can look at, the first instruction means that you are moving A into that. So it means that the first one, in the first instruction, 25A will be having 25H. Then R2 is not affected. In the second instruction, A will be having 25H and R2 will be having 34H. And then we are being told add R2 to A, and then the result, as we had said, will be stored in A again. So it means that we are going to add the two of them. It means that at the end of that, A will be having 34H plus 25H, which is 59H, and R2 will still have 34H. So in this case, somebody can still ask you, at the end of this program, what will be the content of the accumulator? Then the content of the accumulator will be 59H. So the trace table will always help you to know the contents of the various memory locations at the end of the execution. So if you do your trace table correctly, you will be able to know the content of each and every memory location at the end of the execution of that particular of a given program.